So we are in this chapter on secure hash, cryptographic hashes. And the most common algorithm is SHA-1. SHA stands for secure hash algorithm, right? And it is a standard. This is a standard from NIST, like all other security standards that we have seen so far, and several features that we'll see. NIST in the United States is the one that sets the standards, and then mostly they're followed by other countries as well. So, okay. All right, so SHA-1 is 160-bit long. All right, and it uses 512-bit blocks using 32-bit operations. There are three parameters. How long is the hash? What is the block size? And what is the operation size? At some point, people used to do 8-bit operations, then 16-bit, 32. Now we are in 64-bit mostly. But when SHA-1 was done, 32-bit operation was most common. So that's what it uses. And it uses 512-bit blocks. So it handles that many bits at a time. If you have big messages, which generally are the case, you will break them down into 512 bits. And then the output would be 160-bit long. Now 160 seems like a compromise because what is 160? I mean, 160 is 160 divided by 8 would be 20 bytes. 20 bytes doesn't seem to be a multiple of what we would generally want. I mean, we have 32-bit CRCs. And so some things has to be multiple of, it is multiple of 32, but multiple 5 somehow doesn't seem like. But anyway, that's what it is. And the reason is that you don't want it too long. At the same time, you don't want too short. 160-bit provides you protection of 80 bits, basically half of the size. Remember, if you have n bit something and you want to match it, you need n by 2, 2 raised to n by 2 attempts. So this is 80-bit, which was big enough not to be feasible and small enough so that you can compute it. So anyway, 512 bits, basically what they do is they convert that into 5 times 512 bits. So every word is basically copied 5 times as follows. The nth word is exclusive R of n-3, n-8, n-14, and n-16th word. So suppose you want to find out what is 50th word. For 50th word, you will have to do 57 and all those numbers. And those words themselves are calculated by the same formula because all you have is 512 bits, which will give you, divided by 32, will give you how many? 16 words, right? And out of those 16, you have to make 80 words. So 17th word is calculated like this, 18th, 19th, 20th, all the way up to 80th word is completed like this. Okay? And before they're exclusive R, they're not just exclusive R, they're shifted by 1 bit. So there's a little bit more complication in getting. So basically, at the end of this process, you have 80 words, 32-bit long words, right? And you handle them 160-bit at a time. So you take 5 words at a time. So you have 80, you have to do 16 times something, which I'm going to explain here. The first 5 words will go through, then next 5 words will come in and so on and so forth. So the thing is, no, let's see, it's 160 times 5 is 800. 160 times 5 is 800. (16 words of message, which is 512, and Okay, anyway, so let's just see what happens here. So here we have 5 words, A, B, C, D, and E, right? And all we do is, we take all these 5 words, take it through a very complicated function. Now, complicated function is defined in the book. You can go through that, but it's not critical. It's just like, other things that we have seen in DES and AES. So you somehow, with that, you come up with one word, which is, come up with a result, which is 32-bit long, and so you get A. So A, B, C, D, E combined give you an A. And then all you do is copy A, copy B, copy C, D, and so on and so forth. So this kind of thing goes on. At the end, you will have 160-bit left, which would be the C, which would be the hash. That would be the final hash. And so this is not very different from the other things that we have seen, like AES, both AES as well as DES, that there is this complicated function, and then at the end, this A will move to the next position, and so on and so forth. And whatever is left is 160-bit hash. Okay. Any questions about that? Notice that there is no key in this case, right? So this is not something that is any way confidential or anything. Anybody can calculate SHA-1 and anybody can verify SHA-1, just like MD5. Anybody can calculate MD5 and anybody can verify MD5. So all it does is ensures integrity, right? The message has not been changed, and that's it. The next chapter will talk about how to do better than this.
So I have a question on the first bullet point. So this means that we have 512-bit block as input, which is in a 160-bit hash, and 32-bit operation means we take 2.
32. These are 32-bit operations. Yeah. These are each 32-bit. So when you do this function, you are doing 32-bit A, 32-bit B, 32-bit C, 32-bit D, 32-bit E. Okay. SHA-2 basically extended this. 160 is not enough, so they made 512 and 256. Now 256 still uses 32-bit operation and 512 uses 64-bit operation. And these use different amount of shifts and addition and all that. But from 256 you can also get 224, and from 512 you can get 384. So what that is that if you want to get SHA-224, all you do is you do 256, but ignore the least significant whatever number of bits are left. I think 26 bits. Sorry, 225 plus 26 plus 6. 32 bits you will leave here, and in 384, 512 minus 384 bits of least significant bit will be discarded. And so you just send that much. Okay. And the reason people want 224 is because its strength is just half of that. What is its strength? How many bits? How many bits is the strength of a n-bit hash? Half, n by 2. So 224 has 112, which is the strength of triple DES. Right? So that is the reason for 224. Anyway, so this table here summarizes all these SHA-0, SHA-1, SHA-2s, Now SHA-2 actually really has two versions, 256 and 512. And so the internal state just besides SHA-1 was 160 bit. Here it is 256 bit and 512 bits. The block size is here 512, which continues on 256 but becomes 1024 in SHA-512. The maximum size of the message is 2⁻64 - 1, and this one is, that number there, 128, and so on. Okay? The number of rounds, the operations, and the collisions, etc. Now, just to show you the complications of 512, SHA-512, which is actually in some sense the latest, actually there is one more later than this, but this is latest in use, is that you take the message, append zeros, and append the length to make it multiple of 1024. Okay? And this business of appending zeros and the length you will see in other methods later on as well. But anyway, so the padding is not just zeros, it is zeros followed by the length. One followed by zeros followed by the length. So then you convert, and then you break it down into 1024 bit blocks. Okay. Then you do some function. Actually, we will explain the functions in a minute. You do a function and you use an IV there that will give you, after adding that number and using that in the function, you get H1, the 512 bits. Those are fed back to the next block, and then those are fed back to the next block, and so on and so forth. At the end, whatever you get is the hash. Okay, so this is the hash, and if this matches, then everything else will match. If this doesn't match, then we don't know where the problem is, but we know that there's a problem.
So here we have so many input message blocks, but only one hash code. Or they are all hash codes.
The H1, H2?
Yeah, because we have M1, M2 to Mn.
Yeah.
There's so many message blocks.
Yeah, but the thing is, you might have, let's say, so that's a good question. So question is, if you have, let's say, 100 message blocks, so message is 100 times 1024, right? How long is your output? Output is always exactly 512 bit long. Regardless of the length of the message, you just get the one thing. That's why there is this feedback. Because if there is any error here, that will change that one. So the last output is the one that is you send out. You don't send out the intermediate ones. Does that answer your question?
Yeah.
All right. And so in the hash, actually, this is also another thing which is common, is that basically you keep using the previous block's hash, and then you just send out the last one. Now the round function, if you want to see the complication, is as follows. So as we said, this is a 64-bit word, and we have 1, 2, 3, 4, 5, 6, 7, 8. 8 times 64. It's 512. So this is basically your hash. This is your output. The input is coming from here. And several constants are coming from a table here. So anyway, so what you do is you take A, B, and C and apply the majority function to that one. You take E, F, and G and multiply CH, conditional function there. Okay. And then this is a addition operation, right? And then so on and so forth. So what is the conditional function? If you take 3 parameters, you can say 3 bits, then the conditional function says that E, F, and G is true. Sorry, if E, then F, else G. So whatever, if E is true, then you send the first parameter out. If E is false, then you send out the second parameter. So you do this bit by bit, right? So E, F, G, you take 3 64-bit words, and then you send out a 64-bit word whose bits are calculated like as follows, bit by bit. It's clear what is, and actually in logic, this is simply E and F exclusive or not E and G. If you do that, that's exactly what it is. If E, then F, else G. Okay? So that is the CH function, majority function. Majority function is simply ABC is true if 2 of the 3 arguments are true. So again, you do bit by bit. You have 3 bits, A, B, and C. If 2 of them are 1, then the output is 1. All right? In logic, that would be A and B exclusive are A and C, exclusive are B and C. Okay? So here's the thing. I mean, I didn't give this in the homework, but this very well can be in the exam. I could give you 2 64-bit words or 3 64-bit words and ask you what is the majority function result. Okay? So make sure that you understand this kind of stuff. And a little bit more. You see these plus sign, before that there is a sigma 0 and sigma 1. Sigma 0 and sigma 1. So you take word 0, word 1, word 9, word 14. 1 and 14 go through sigma 0 and sigma 1, and then they are added. So sigma 0 means rotate by 1 bit x, and then rotate by 8 bit x, and then shift right SHR by 6 bits. Here it is 7 bits. So rotate means the first bit goes back to the last position, right? If you rotate left or whatever, right? Or rotate right means the last bit comes back to the first position. So rotate right is like that. And shift means they just fall off. So basically they don't come back into the first position. So that is the difference between shift right and rotate right. Is that clear? What is the difference between shift right and rotate right? Rotate right, the bits come back. On the other hand, shift right, they just fall off. And sigma 1 is rotate right, and shift right, again. And addition is modulo 2 raised to 64. What that simply means is that it is a really 64-bit word addition, except that there are no carries further than that. I mean, you don't carry on from one word to the next word. Anyway, that's all about 512. So the key thing to notice is that these are complicated functions, and these are this, and I could have done the same thing for, actually there is a similar diagram for SHA-1. I did not go through that, but this one shows you the complexity, and generally these are designed for the hardware anyway. So people build these circuits and get the hash. SHA-3 is out now. But even though the standard is out, right now there is not much need because 512 still is good enough. But getting ready for the future, NIST announced a competition in 2007, 7 years ago. They announced the result in 2012, 2 years ago. So we know what SHA-3 is, but it's still not much in use. So SHA-2 is what basically is coming in, and SHA is what is mostly in use, SHA-1. So SHA-3 basically will replace some days 2 and 2. It's similar to 2, and it can process small blocks, etc., etc. Now, these criteria are mostly of historical interest because all of these have been met by the selection. So security should be close to the theoretical max for the hash sizes and cost in memory, time, etc., etc. Basically, is that this should be easy to compute and simple and so on and so forth. But anyway, SHA-3 is out. Those of you who have to do any development, they can go to NIST and get the documentation and implement it. But right now, SHA-1 is what is used mostly. So that brings us to the end of this hashing stuff. And the key summary points are 5 points. First is that hash functions are used to get a digest of the message. So you get actually you can call it digest, you can call it summary, you can call it a CRC kind of thing. And it takes any size input and produces a fixed size output. And the output is, because it is hash, it's pseudo random, so that it basically, if you had a table of that size, it will fall evenly on the table. And the cryptographic hashes are different than CRC in 3 respects. First is they are pre-image resistant, second image resistant, and collision resistant. Pre-image resistant means you cannot calculate the other way around, you cannot invert it. Second means you cannot even find another message that has the same result. And collision resistant means you cannot find any 2 messages of anything. You're not even given a message, but any 2 messages which are the same thing, same hash. So those are the 3 properties. Now CRC does not follow any of these properties, by the way. CRC is very easy to change. CRC is very simplest thing in terms of what we are talking about here, is that if you wanted to change it, you can do it on a piece of paper. You can just do it in your mind and change the function, and you can figure out that what the new message should be. So the bits can be inverted very easily in the messages if you are using CRC. So this is why we need cryptographic hash. There is no really security in here, in the sense that there is no key involved, but they are collision resistant. And they are not easy to invert, whereas CRC is very easy to invert. Cryptographic hashes are used for, by the way, I have written a paper some long time ago, 20 years ago, when we were discussing about what is the best hash function. So our conclusion was in that paper that the best hash function is CRC. Okay, this is 1980s, sometime like 1984, 85 time frame. So the best hash function is CRC, but it doesn't have those 3 properties, right? If you didn't want those 3 properties, then that is the easiest hash. And it's very easy to calculate too. I mean, you don't have to have 32-bit CRC. You can have 8-bit CRC, 6-bit CRC, 12-bit CRCs. So there are CRCs available for all kinds of lengths. So if you're writing a simple program somewhere and you need to just put the data into the table and you're looking for a hash function, look into CRC. All right. So having done that, now let's see. So cryptographic hash function have these 3 properties. Cryptographic hashes are used for message authentication, digital signature, and password storage. So we already saw how they are used for password storage. Digital signature will come in few chapters, and message authentication is the next chapter. So we'll see that in the next few chapters. Now SHA-1 produces 160-bit output. SHA-224 produces how many bits output? Anybody remembers? This is today's lecture. How many bits come out of SHA-224? Nobody was paying attention? 224. So the number here are the size of the output. Right? There are 3 things that you have for a hash. First is the output size, the input size, and the word size, right? So SHA-1 uses 160-bit for the output, and the word size was 32, and the input size was 512. And for these, actually, similar things apply, except the output is actually 256 bits, and we just take 224 out of that, 256 bit. And this one is 512, and we can take 384 out of that. So those are the output sizes. SHA-3 has been designed, but not yet required by any method for any, so they're not required yet. Homework is actually very easy. Homework is that this is a hash function, and you can calculate this hash function. But you have to find out whether this is collision resistant, pre-image resistant, and second pre-image resistant. And so you have to show the counterexample if it is not. Okay? So first you can use this example to calculate it, and then you can think about it as to how you can find something else which has the same hash. How you can find two numbers that have the same hash. Any questions about the homework? Okay, I will leave that homework for you guys to think about, and we move on to the next one.